Hello, everybody, and welcome to another wonderful day of chemistry. Today, we're going to be talking about intermolecular forces. They are found in all things, they flow through all things, and they hold the universe together, and I mean that quite literally. But before we talk about them, we need to actually define what the heck intermolecular forces are. So from the simplest perspective, these are going to be the forces that interact in between two different molecules and will make them attracted to each other. Now, one of the important things to make note about intermolecular forces is that all interactions between molecules and atoms, either inside a molecule or in between molecules, are entirely controlled by the fact that positive and negative charges attract. These are collectively known as Coulombic forces. Negative likes positive, positive like negative. So in a covalent bond, these atoms are held together by the fact that we have a buildup of electrons in between the two atoms. And so the two nuclei move towards the center of the bond. Now, if you have something like an ionic bond, well, what happened is that one of the atoms stole all of the electrons. And so the nuclei says, ooh, I want to hang out with those electrons. And that's what pulls the system together. However, it turns out most bonds are somewhere in between. So what tends to happen is that the electrons are mostly located on one atom instead of another. Now, when this ends up happening, it means that this one atom has a partial buildup of charge. So it has a slight negative charge, and this atom has a slight positive charge. So this helps pull the atoms together. But one of the important things is that this also means that since this atom has a partial negative charge, that other atoms with a partial positive charge out here in the greater sphere of the universe will want to hang out with that negative charge. And this will help bring molecules together. Now, one of the things that's worth noting is even if you have a nonpolar molecule, so something like this, what can happen is these electrons will slosh from side to side. And this can temporarily generate a positive or negative charge. And this is why all atoms and all molecules can have some form of intermolecular forces, because we can at least generate a negative charge on a system at some point. And so anytime we're looking at an interaction that is any two molecules interacting that isn't strictly ionic, these are said to interact through van der Waals forces. So this is essentially positive charges being attracted to a partial negative one. So in order to evaluate the strength of all of these potential van der Waals forces, we're going to need to use two key metrics. The first of which is fairly straightforward. We've seen it before, but it's been a while. And this is the dipole moment. When we're talking about the polarity of a molecule, this is what we're talking about. This is the idea that one side of the molecule will be more negative and one side will be more positive. So if I'm looking at something like water, I have positive charge up on the hydrogen atoms and negative charge over by the oxygen atoms. However, some molecules don't really possess much of a dipole moment. These are our nonpolar molecules, at which point what we really care about is going to be the polarizability. So if a molecule doesn't have a dipole moment, how easily can I make a dipole moment? Can the electrons move from one side to the other? Can I generate a positive and a negative side of my molecule, even if temporarily? So let's go ahead and start by looking at that dipole moment first. So when we look at the polarity of an atom, polarity of a molecule, it's largely driven by the electronegativity of the atoms involved. So hydrogen kind of marks the neutral point. So if I put it next to lithium, the hydrogen is going to tend to build up most of the electrons because lithium is very poorly electronegative. However, if I put hydrogen next to fluorine, fluorine is very electronegative. So all the electrons move over to the fluorine. And both of these represent polar molecules. All the electrons have moved to one side. Now, if I've got a polyatomic molecule, what I'm looking at is how unevenly spread these electronegative atoms are. So if I have something like chloroform, all the electronegative atoms are on one side, all the poorly electronegative atoms are on the other side, so hydrogen. So this means that one side, hydrogen, is going to be relatively positive, and one side, the chlorines, is going to be relatively electronegative. This means that if I start putting multiple of these molecules together, we're going to find these chlorines on one molecule next to the positive charge on the next. Now, this gives us the idea of dipole moments. So this is just going to be a measure of polarity. Which side is positive? Which side is negative? Can I line up the charges? However, oftentimes I'm going to have a neutral molecule or a neutral atom. Say, think about something like xenon. It's very big. It has no charge. However, because it's very big, I can slosh those electrons from side to side. So if I put a positive cation next to this neutral species, all the electrons on the molecule are going to say, ooh, I want to hang out with you. And they move over to the positive side. Now, this generates a positive side on the molecule itself, which can attract other negative ions or molecules, or just, again, another partially charged species. So molecules are going to tend to be more polarizable if they contain larger atoms with similar electronegativities. So something like xenon is going to be a lot more polarizable than krypton, than argon, than neon. Because again, the xenon is going to be larger. This also holds in molecules themselves. So if I have something like hydrogen sulfide is going to be much more polarizable than water. Oxygen is fairly electronegative, and it's fairly small when you compare it to sulfur. Sulfur has a full 10 more electrons. Those electrons are sitting much further out. So it's going to hold on to those valence electrons a lot more poorly, which means that those electrons can slosh from side to side a lot more. And so it can generate these partial negative charges much more easily. However, one of the things you may note is that polarizability and dipole moments can be in opposite ends. And we're going to be evaluating which ones will generate stronger intermolecular forces next time. So now that we've seen how molecules can generate negative and positive charges, what happens when I start throwing them together? So if I start throwing multiple molecules together, they're going to start arranging the positive and negative charges, like if I throw a bundle of magnets into a pile. One positive charge will interact with one negative charge, but it can interact with the negative charge in a direct on sort of view or from a side on perspective. And what you start doing is building up big lattices. And this is how we end up producing solid structures. And in liquids, you have the same sort of structure, but it's much more fluid. They can start flipping around and moving. And you'll see this. Some arrangements of magnets are going to be very reluctant to essentially pushing on it. Others will be much more fluid because they're able to quickly switch around these interactions. Now, one of the important things is that this can occur whether we're looking at polarizable molecules or very polar molecules. And if we understand the nature of the positive and negative charges, their strength, and of course, their shape, because that will control the form larger structures take, we can start to predict what sort of structures we're going to form and their stability and how they interact. And this is going to be a large goal of ours going forward. So next time, we're going to be looking a little bit more specifically about the ways we can generate positive, negative interactions as we talk about all of the types of intermolecular forces. Until then, take care.